Okay, hi guys. So in this lecture, we'll be starting on collision frequency. So let me write down the heading first. This is collision frequency, which is nothing but number of collisions taking place per unit time and per unit volume. Okay. So before that, let me just brush up from the previous lecture that we saw n star as number of molecules per unit volume. Okay, and we saw z star as number of collisions made by a gas molecule in unit time. Number of collisions made by a gas molecule in unit time. And I hope you also remember that we discussed the volume of the volume swept by the colliding particles, in which we considered something like this. We considered 3 molecules, and from here we defined volume swept from the collision as pi sigma square. So from here we'll be building on and seeing how can we define the collision frequency. The collision frequency is total number of collisions taking place. We can also write total here. It's optional. Total number of collisions taking place per unit time and per unit volume. So Z star only tells us number of collisions made by a single molecule in per unit, single molecule per unit time. Okay. So what would be the total number of collisions taking place? So total number of collisions would be so we only considered one of the moving particles in this case, and rest all were stationary. Okay, so as all rest were stationary, we were only taking into consideration in Z star then the total number of collisions taking place when this moving particle was colliding with different particles in the vessel. Okay, but now we are considering that what will be the total number of collisions when all the the molecules would be colliding with each other. So in the previous lecture we saw that when two molecules were moving, we considered that the average angle we'll be considering between them would be 90°. So in that case we can consider that u relative was root 2 times u average. Okay, so we'll be just utilizing the fact. Now we'll be considering that all the gas molecules are moving, and what would the total number of collisions made by the all the gas molecules moving and colliding with each other. Okay, so as you can see that this for collision of this molecule with the rest two, we only also considered the collision by this molecule with this molecule and by this molecule with this molecule twice. Okay, so we'll be writing that the total number of collisions taking place would be nothing but, let's denote it by Z11. So it would be, now we'll come to this half part later, but let me first write down the other terms. So we know that Z star is the number of collisions by a single gas by a single moving gas particle, gas molecule in unit time. So when we multiply Z star with total number of molecules per unit time, we will get total number of collisions made by a gas molecule per unit volume and per unit time. Okay, but we also know that the number of collisions are just doubled in this case. Why? Because this molecule has already collided with this molecule, and this molecule has already collided with this molecule. So this molecule would only be considered, so this molecule in collision is considered twice because of once the collision with this molecule and once the collision with this molecule. So total number of collisions which we are considering would always be doubled in every case. Okay, similarly I can say that when this, let's say this was X molecule, this was Y molecule, and this was Z molecule. So when this X molecule must have been collided with different another moving molecule, and when this Z molecule would have collided with another Z molecule, we would be counting when we multiply actually Z star with N star, this quantity twice, because this actually counts the total number of collisions made by this molecule and made by this molecule. So the total number of collisions would be 2 in this case, but the total number of collisions, but the actual number of collisions that was happening between Z and Z star, this is Z star molecule, would only be 1. So every time this, when we multiply Z star with N star, every time this quantity is doubled, so we need to half it. So that's why we are putting half. So now Z star, which was only the number of collisions made by a single gas molecule in unit time, when we multiply it with all the number of with the number of molecules per unit volume, we will be getting total number of collisions which happened per unit time and per unit volume. Obviously that quantity would be doubled, as we'll always be considering single collision twice, so we'll be putting a factor of half here. Okay, and in this case U relative would be considered, and this would be √2 of U average, because we are considering all the particles moving. Means in the collision, both of the two colliding particles would be moving. Had it been that the case that one of the particles was at rest, then we would have not considered √2 factor here. So Z11 would be half of Z star would be √2 U average pi sigma square N star multiplied with N star. So this would be 1 by √2 U average sigma pi square pi sigma square rather N star squared. This would be Z11. And let's discuss another case when we are dealing with different types of gas molecules. Different types of gas molecules. Okay, so here let's consider that we are taking into two gas types, gas A and gas B, and we are considering that gas B particles are stationary. Okay, so again we can write that Z11 rather Z12 in this case, because Z11 represents the molecules of same types, but Z12 would represent that Z1 is having collision with type of gas, second type of gas, which is B in this case. So this would be nothing but, so first let me draw what would the collision diagram look like. Suppose this is gas B molecule and this is gas A molecule. So this is gas A and this is gas B, BX molecule, and let it be BX molecule, this is A molecule, and let it be BY molecule. Okay, so sigma in this case would be, let's write sigma AB, which would be nothing but radius of B plus radius of A. So in this case we can write that, and we are considering that B is stationary, so we are considering that A is moving with some velocity U average, let's suppose. Okay, so let's first write what is the total number of collisions by a single A particle in the vessel containing a mixture of A and B. So that would be nothing but ZA. Okay, so this is total number of collisions taking place by this single A atom in the complete vessel. Okay, and what would be the total number of collisions by taking place between all the A particles with B particles? So this has to be multiplied with N of B star. N of B star is nothing but total number of molecules of B present per unit volume in the vessel. Per unit volume is the volume saved by the colliding particles. And do we need a half factor here? No. Why? Because every time a collision is occurring, a molecule is colliding with two different molecules of B. So total number of molecules would just be this. Okay. And ZA would be nothing but pi sigma AB square times U average. We won't be writing root 2 factor here. Why? Because the B particles are considered at rest, times Na star. Na star is the total number of molecules of A present per unit volume of the colliding cross section. Means per unit volume is the volume served by the colliding particles. So this is the total number of collisions which can take place by one of the gas A molecules. That has to be multiplied with all the number of molecules of B present per unit volume of colliding particles. This has to be multiplied with NB star rather. So this would give us the total number of collisions taking place by all the different by all the molecules of type A gas with molecules of gas B. Okay, where we can write Na star is number of molecules of A per unit volume, and NB star is again number of molecules of B per unit volume. Volume would remain the same because volume considered is the volume of colliding particles. Okay, so with this we come to the end of this lecture. In the next lecture we'll be starting on mean free path. So till then, good luck and goodbye.